Okay, here we have a problem that requires some exponential modeling. Wood is a sustainable and renewable natural resource if properly managed. A lumber company has 1,200,000 trees. They plan to harvest 7% of the trees each year. At this rate, how many years will it take to harvest half of the trees? This is an excellent problem for exponential modeling because it is decreasing by a set percentage each year, as opposed to decreasing by a certain amount of trees each year. So since we're decreasing by a set percentage, we can go ahead and set up an exponential model. We know what our initial value is. We can create our decay factor since we have this percent decrease with this. And we know what value we want to reach. If we want to reach half of the trees, if there's 1,200,000 trees right now, half of that would be 600,000. So with that information, we ought to be able to model this scenario with an exponential equation. Let's go ahead and model this scenario with an exponential function. T of n equals a times b to the n, where T of n stands for the number of trees remaining after n years. N is the number of years. A is our initial value or starting amount of trees. And B is our growth or decay factor, in this case our decay factor. So T of n, our number of trees remaining after so many years. We'll hold on to that one for a second. We'll plug in a number here in a moment. But let's just set up the scenario. We know our initial value of 1,200,000. Our decay factor should be 1 minus our percent decay as a decimal. 7% decay would be 0.07 to the n. Simplifying that a bit, I have the function T of n equals 1,200,000 times 0.93 to the n. So there I've created a function to model the number of trees remaining in any given year with this percent decay outlined in this question. Now, to go ahead and actually solve this, we want to know when the value, or how many years it takes for the number of trees to be cut in half. I kind of commented on this in the earlier portion of the video, but half of 1,200,000 is 600,000. So what I'm going to do is I'm going to plug in 600,000 for the number of trees remaining after n years, and then I'm going to solve for n to figure out how many years that was. So 1,200,000 times 0.93 to the n. Now, the first step when solving an equation like this is to go ahead and get rid of the initial value. We're going to divide both sides by 1,200,000. And when I do that, that would cancel out over here on the right side, and over there that would make half, or 0.5. I'm not going to write that. I'm going to save some space. I'm going to write it as a decimal since I have a decimal over here just to be consistent. So I have 0.5 equals 0.93 to the n. At this point in time, this is where I would want to take logarithms of both sides. Let me move over here a little bit. So I'll go down here still. So I have log of 0.5 equals log of 0.93 to the n. Now that I've taken logarithms of both sides, I can take advantage of that power property of logarithms to move my variable n, which is currently trapped in the exponent, down in front of this logarithm connected by multiplication. That would give me log of 0.5 equals n times log of 0.93. And then finally, to finish solving this for n, I would need to divide both sides by the log of 0.93, and I would get that n is equal to log of 0.5 divided by log of 0.93. At this point, I need to go to my calculator to compute this. This problem is asking me to predict a number of years rounded to the nearest hundredth of a year, so that's 2 decimal places. So I'm going to go to my calculator now. I'm going to go ahead and compute this division of logarithms, round that to 2 decimal places, so I can know approximately how many years it will take this population of trees to go from 1,200,000 down to half, which was the 600,000. Going to my calculator to compute log of 0.5 divided by log 0.93, and that is equal to 9.55 1, 3. So rounded to 2 decimal places like it asked me for, the nearest hundredth, that'd be 9.55 years. So just a little more than 9.5 years until this population of trees from 1,200,000 is down to 600,000.